So this session now we're turning from science to talking more about missions and technologies and whatnot. So I'm going to sort of try to set the scene by talking about some previous studies and missions, polar missions. So I'll talk about, this is really an awkward place. Okay, you can't really see what you're talking about. Do it that way. So I'm going to talk very little about why we need the polar perspective, because that's obviously been covered very well in the last day and a half. Then I'll talk about three different types of approaches towards getting spacecraft to the polar regions. The conventional propulsion with Jupiter gravity assist, such as what was used for the Ulysses mission. Then I'll talk about solar sail and spend a lot of time on the Solar Polar Imager Vision Mission study, which I led in 2004. And then finish up by talking about how you might do this with a constellation of CubeSats or microsats. Is it not working?
No, the pointer was not a problem.
Okay. Now the problem is that this is so small. Why is this thing so teeny?
Oh.
Okay. Okay, so why do we need the polar perspective? We've heard a lot about this, so I'll just go over it quickly. Obviously, we want to measure the, hang on a minute.
It was easy enough to do, but hang on, sorry. Easy, if you clone displays, it'll do it. I think it's meant to be a feature, but sort of an annoying one.
I'm okay with presenter view, but if you want
You
to
want
do...
round?
No, full screen is fine, too.
Okay, sorry. I'm sorry.
Okay.
Let's try this.
What happens if you just go full screen here? Same thing. Okay. All right.
Okay,
Well,
sorry, I'll try.
that's the way what it is. Okay, so I can barely see what this is. Okay, so we want to measure the time-varying flows in the polar regions, of course, the convective flows, differential rotation, et cetera, and look at these flows with depth.
I'm very sorry. I'm like flubbing my tech assistant like crazy
okay.
completely, but the display window is blocking everything behind you. So,
Oh, great. Okay.
yeah, no good. Yeah, I was hoping that was going to do the trick, but it
Gee,
really
it's funny. I think I checked this before, and before lunch it was fine.
All right, don't worry. This doesn't count towards your time.
Okay, and there's no way to make that bigger.
Does anybody know how to make this bigger? Because it's not at all obvious to me.
Okay, I can barely read it.
It's
Okay.
the thing you don't see that's small.
All right. So, okay, so we want to measure all of the flows in the polar regions. Preferably, of course, we'd like to go all the way down to the tachocline. Want to measure the magnitude of the polar magnetic fields and how they evolve in time. Want to look at the chromosphere and the low solar wind outflows in the polar regions. Of course, we'd like to be able to monitor CMEs from high latitude, as we've heard that. Vic talked about that a lot, and for space weather purposes and whatnot. And also look at the total solar irradiance from the polar perspective, as was discussed also. And, of course, measure the variations in the magnetic field, the solar wind, the energetic particles, and all of that at high latitude, closer to the sun than Ulysses. So, but I want to say that, so this is a lot of different objectives, and it's very important to keep in mind that how well you can address any of these individual objectives will depend a lot on the polar orbit details, on the inclination of the orbit, particularly how much time you spend at high latitude, et cetera, and of course also the instruments. So the first polar mission, of course, was Ulysses. This was part of, originally of an international solar polar mission that started in 1979, and Vic also mentioned this earlier. There were supposed to be two spacecraft that would both go into 6-year elliptical orbits of 1 and a little over 1 AU by 5 AU as going to Jupiter. And the ESA spacecraft survived. That became the incredibly successful Ulysses mission that gave us what we now know about the 3D heliosphere. And the NASA spacecraft was going to have similar in situ, but also was going to have a coronagraph and X-ray and EUV, and that was canceled. So this mission, as I said, the orbit is shown here. It went from Earth straight out to Jupiter. It was launched from the space shuttle. And then Jupiter is the only planet that's heavy enough to use to get a gravity assist where you can actually get all the way over, significantly out of the ecliptic and over the pole. But this does have, if you don't do anything, it's a 6-year orbit, which is kind of long. And if you want to have a shorter, more circular orbit, then there's other things you can do. You can add gravity assists and burns at the perihelion. And you'll hear about 2 concepts this afternoon. Jeff Newmark and Don Hassler will talk about missions that use variations on this. The one that was part of a roadmap mission in 2003 was called Telemachus, and it used not just a Jupiter assist, but in order to it couldn't go directly to Jupiter and stay on kind of the cost. So it did a couple of flybys, Venus and to Earth, and then also perihelion burn to get an orbit that was eventually, after 8 years, it got into a science orbit, shown here, it was 0.2 by 2.4 AU. So much smaller than Ulysses, 1 AU by 5 AU orbit. And the period for this orbit was 1.5 years. The polar pass was at 80 solar radii. But in this 1.5-year orbit, only 5 weeks were spent above 45 degrees latitude. But briefly, the science was going to be when they were over the poles, they were going to do remote sensing, some helioseismology, and also look at some imagers. And then otherwise, they would be looking at the properties of the solar wind, like Ulysses did, kind of talk the kind of science that Heather was talking about. And there's the reference for that. So it would be very similar to Ulysses, except for when it was doing the imaging over the poles. But of course, much closer to the sun. Okay, then I spend a lot of time on, this is the Solar Polar Imager, and also Polaris. This was a roadmap mission, but it started as a study by Marcia Neugebauer in 1998, and then I led a vision mission study starting in 2004 of this. Then this decided to go to France. It was picked up by Thierry Aperchot, who's here, as proposed as a cosmic vision mission. And there's the reference there, and a lot of work was done on the solar sail technology in Europe as well as in the US. So what is this mission? So it uses a solar sail. And solar sail, first you spiral in closer to the sun, which increases the radiation pressure, staying in the ecliptic. Then you go to 0.48 AU, and then start cranking the orbit up, and you get higher and higher depending on how long. So it was and we picked this 0.48 AU because that's in 3:1 resonance with Earth, so that the spacecraft is always in view of Earth and you can communicate whenever you want. So it's 2 to 3 years to get into that, about 0.5 AU, and then another 3 to 4 years to crank up. And the final inclination for this study was 75 degrees, and I'll talk more about why that is. And the sail was on the order of 150 to 180 meters on the side, so it's a pretty good-sized sail. And there's the list of the instruments. It has instruments for all the science we've talked about, I think, except maybe not an X-ray, soft X-ray, but obviously the coronagraph, EUV imager, spectrometer, solar wind instruments, magnetometer, and total solar radiance. And in the Polaris version, it also had plasma wave. And it should, there I have the list of the data and mass, et cetera. So why was this such a popular mission? It's because this orbit is really wonderful for many different kinds of science. For helioseismology, it has very long periods at a constant radius, and 29% of the time in the science orbit is spent above 60 degrees. And as you heard this morning, above 60 degrees is kind of a really good place to get good observations of the polar region. Since it's on this 3-1 resonance, you're doing a complete polar orbit every 4 months. So you get a good look at how the flows and magnetic fields are evolving in the polar regions. And then you also, since if you have another instrument in 1 AU orbit, you can try to do stereoscopic helioseismology. Of course, this is a really good orbit for looking at the magnetic fields, since you have a lot of time above 60 degrees. And follow the evolution of the magnetic fields. Again, every 4 months, you're getting a good long look at the flux in the pole. And you get a different view that allows you to follow active regions much longer. You get the polar perspective of CMEs and other structures in the solar wind. And for looking at the solar wind, you're scanning all latitudes every 4 months at half an AU, so you're closer to the sun and less evolution. Since it's always the same radius, you're able to separate the radial and temporal evolution. So just to kind of make a quick comparison of whether you use the SPI orbit or the Telemachus conventional, both of these take a long time to get to the science orbit, 7 or 8 years. The big disadvantage of solar polar imager type orbit is that it's not yet technologically feasible. Then we'd hope that the technology for large solar sails would develop more rapidly, and it hasn't. Les will be addressing this in his talk. But the disadvantage of the other orbits is that the resulting elliptical orbit tends to not spend a lot of time above 60 degrees, as opposed to 29% for SPI. So Telemachus, for example, only 6% of the orbit was above even 45 degrees. So solar orbiter, we said, will only go to 30 degrees, and that's taking 9 years using Venus gravity assist. Okay, so I'll make a slight shift here and talk about the lessons learned from the SPI vision mission study. So we've talked a lot about how a NASA mission has to have discovery science, breakthrough science, some very important science if it's going to be selected. And it's clear to me, at least, that the helioseismology, which including the polar regions, is definitely discovery science. But it's very important to remember that different helioseismic objectives are going to require different amounts of time at high latitude. In our study, we found times ranging from 8 hours to 72 days, depending on what you wanted to measure. And in fact, we said we wanted to measure flows down to the tachocline. And that's very ambitious, and that's what drove the requirement for a 75-degree inclination orbit, because that gives you enough time above 60 degrees. But I think that there's a lot of other discovery class science that can be done without having to measure the flows all the way down to the tachocline. So I think it's important when you're looking at different mission concepts to really quantify exactly what helioseismic objectives can be achieved for different amounts of time. So it's not enough to say what latitude, but you have to say what latitude and how long. And to drive this home, So this was arguably, seismology was based on discussions with Sasha Kosovachev. So, and this was done probably pre-HMI, so these may change. And, but just to give you a rough idea, the local helioseismology has different kinds of observations. If you want to get surface and subsurface flows, you tend to need uninterrupted observations, but they're only like 8 to 24 hours. But if you want to get down to the tachocline, this is where you start requiring, like this was 17 days above 60 degrees to get that. The global modes depends again on what, 36 days maybe for torsional oscillation or other global variations, and much longer, again, if you're trying to get the really low order modes that propagate into the polar regions, those also took very long times. So we had like 3 different observation modes that we came up with, all that had to have Dopplergrams on a 1-minute cadence. None of them super high resolution, either 512 or 256, and you can see them there. So there were some that were short, 8 to 24 hours, others that were 7 to 14 days, or the longer ones for the really deep flows. But I think you can see there's plenty of objectives that don't require so much time above 60 degrees. Okay, getting back now to the approaches for polar mission. More recently, we looked at the possibility of using a constellation of CubeSats or small satellites. And this, the fractionated concept, this is where you put different instruments on different spacecraft. So what's the technology status now for this? Well, we've just launched the first interplanetary CubeSats. 2 are now on their way to Mars. They were rideshare with InSight, launched in May. Also now, there's been solar sail technology has developed for much smaller satellites, and again, Les will talk about this. Here I'm referencing LightSail 1, which is a Planetary Society CubeSat that demonstrated sail deployment, and they have one that will demonstrate actual sailing and sail control, launching on the next Falcon Heavy. So again, this approach is becoming feasible. And I guess Noor made reference to this one concept of a solar polar diamond explorer, and there's a reference there, where put multiple satellites, small satellites, in the same solar polar imager type orbit. But now you can phase them, so if you have 2, you can think of having the EUV and the coronagraph like 90 degrees out of phase. So you can be looking at, everything will be a limb CME, and you can look at the source region. And there's a lot of advantages to this fractionated approach. First, the fact that the solar sails might now be suitable for propulsion for this much smaller spacecraft. And I think there's also a lot of work in the CubeSat world on electric propulsion. The spacecraft requirements become much less if you have your in situ instruments on one spacecraft and your imaging on another. And of course, the whole developing it is each spacecraft, a lot fewer interactions and whatnot. Integration and testing is easier for several small spacecraft. And the constellation can be built up incrementally. You can just start with one and then keep adding them, or maybe you want to upgrade them or whatever. So it gives you a lot of flexibility in trying to get to this someplace where we might have complete coverage of the sun. So, conclusion. So I think there is definitely breakthrough science from high latitude. Solar orbiter, which will reach 30 inclination, will certainly give us our first glimpse. It's going to take a long time to get into a high latitude orbit, polar orbit. But if we'd launched Telemachus back in 2010, we'd be in the science orbit, so it's about time to get started on some kind of polar mission. Ulysses certainly showed it was worth it. And I think there's a lot of science discoveries that can be made from a polar orbit. It has to do with the relationship between the magnetic flux transport and the flows that can be done in moderate amounts of time at high latitude. Thank you.
Okay, we have time for a few questions. If there are any questions for Paulette, please come to the mic. Yeah.
Do you have any comments about durability or reliability of the CubeSat approach? Maybe CubeSat can break very soon, that people say. Any comments on that?
So I think CubeSats or small satellites are going to be improving rapidly. So I'm not necessarily saying this is what we should launch first, but I think this is something that may become very feasible fairly soon.
Any other questions? You can come to the mic. There's one behind you there.
Yeah, how are these CubeSats going to communicate?
So usually they would might have one satellite that was kind of the one that did the communication with Earth, so you'd have different ones that would feed their data to one that was dedicated to communication. That's one concept.
I hate to jump in. I'm the PI of one of the CubeSat interplanetary missions, and we're using the Iris radio, and we have to be within 1 AU of Earth to be able to call home. And then I'm sure there's all kinds of other ways you could maybe do some relay.
So it sounds like that technology probably isn't ready yet.
Well,
unless you had a relay or something. So
two things that I want to maybe emphasize. One, I think Paulette probably properly characterized it in her talk, which is small sats. She used an example of a CubeSat from Marco, but we should be thinking of small sats necessarily. I think that in Angelos's, for example, his payload was not a CubeSat, it was a small sat. And so what they are is they're taking advantage. This is what Don actually mentioned the other day as part of my second point, is these small sats today are taking advantage of CubeSat, of technologies developed for CubeSats, building them up a little bit bigger. When is it a cube and when is it a small? I'm not going to get, to me it's semantics, but is it a 24U or 100U? I don't know. It's some number of some size that's less than a couple of arm lengths, right? And that's small. But the technologies that they're doing are really, that's pushing us to enable those systems to be small. And so of course, aperture is aperture. Eventually, we need something big. So that's one thing. I think we shouldn't get hung up on CubeSat lifetimes, for example. I think that's a red herring. The other thing, which is, again, part of, Vic, your question about technology, I think Don addressed it the other day quite well. We shouldn't get hung up today on what technology. I mean, the optical comm is flying, and it will be flying better. And by the time we fly a multi-spacecraft constellation, I have a pretty good bet that we'll have optical comm. Because as I said, LADI flew it. Went to the moon. Psyche's going to go to this cool primordial metallic asteroid thing. So I just don't think we worry about some of these gory details, and we get what we want to do, what's important for us to do, and then we tell everyone, and STMD can fund the cool technology.
yeah, one way you could sort of think of it, if maybe I should have been saying small satellite, not CubeSat, is it's something that can go as a ride share, something that doesn't require all of the money that we pay for a big rocket devoted to a single spacecraft. Because that's very expensive, as you all know that have done proposals.
Okay, very good. Thanks, Paulette.
This is so annoying. I can't tell. Here's what we probably should have done. I couldn't even read if this works. I should have brought my own computer.
So we're jockeying speakers because I'm introducing Les, and then he's going to introduce me as the next talk. So Les Johnson from Marshall will be talking about his solar sail experiences.
Les, and you're loaded up. Which one is yours?
It says updated right down here. 'Cause I had put one on earlier. All right, very good.
And you're gonna have the same percentage view, hopefully it'll be okay. It's just
Yeah,
gonna
I'm good. I'm all set.
We have lots of pointers now.
Okay, let me make sure this is all working. Yeah, very good. Okay, yeah, okay, good, I'm on. I'm Les Johnson from NASA Marshall. I'm not part of the solar physics community, but I've been following this because I've been working on solar sail technology for a large part of my career, and it's had lots of ups and downs, and I want to apologize to Paulette and everyone else here. I really thought we'd be further along with solar sails. We actually had, early on in my efforts with solar sails, we were on our way to a big space demo in 2009 as a part of what was the New Millennium program. And it was actually one of the missions down selected for study before that whole program was canceled and all the technology money went into Constellation to return us to the moon, and we know how that turned out. So there have been lots of ups and downs for technology, but this is really the time for solar sails. There's been a lot of effort over the last few years, and I'll bring you up to date on where we stand and where I realistically think the technology can be in the near future. Just to remind you, a solar sail works from solar radiation pressure, photon thrust. It's been measured in space. It's been demonstrated in space. It's complicated. And at the Marshall Space Flight Center, I'm the principal investigator for the Near-Earth Asteroid Scout mission, which will be the U.S.'s first interplanetary solar sail mission using a 6U CubeSat spacecraft, which I'll talk about in a few minutes, very similar to the Marco design, where we're actually having as our primary propulsion system after we're deployed by the rocket into space as a solar sail, which over the life of the mission will give us almost 5 kilometers a second of delta V over the life of the mission. So it's a really capable system, and what's enabled solar sails today, in my opinion, for these small missions is the miniaturization of spacecraft, and I'll talk about that figure of merit in just a few minutes. Real quick review of solar sailing. It's not easy. Conceptually, it's simple. You're reflecting sunlight, momentum transfer, you move the other way. Unfortunately, solar sails are not perfect flat plane reflectors, and as a consequence, you have all kinds of issues you have to deal with coming up with your thrust model to determine actually how to get the optimal thrust out of it. We've done a lot of work on that at Marshall, working also somewhat with Langley, and a lot of private companies are working in this area. And it's really complicated. These large sails are not going to be exactly flat. You have to deal with wrinkles, folds from the deployment, variations of the curvature of the sail on the macro, meso, and micro scale, and we've modeled that and we've done testing. I'm going to, if I can get somebody to come up and take this. This is a piece of solar sail material that we're actually going to fly. You want to just pass it around? This is it's a polyimide. It's 2.5 microns of it's what's called CP1 with an aluminum coating. It's roughly 90% reflective in the visible. And this material we've done long duration life tests on. It holds up pretty well in the space radiation environment. It's pretty robust. If you try to tear it, you can. Please don't try. This particular sample has been handled by probably a few thousand people, and it's still in one piece. Fortunately, it's not flu season, so you don't have to worry about anything there with transmission. But it's the kind of material that we're going to fly on the Near-Earth Asteroid Scout, and I believe will be the first generation sails that will fly some of your instruments. So as we look further into solar sailing, another challenge that we really uncovered as we started working on actually going beyond deployment, which is what everyone in the sail community, in my opinion, has been unfortunately fixated upon for years, when they really should have been thinking about, how do we control the flight of this sail? And for the Near-Earth Asteroid Scout project, we've really had to wrestle with, okay, we know how to deploy, how do we control it? And what are the algorithms? What do we have to do to maintain attitude, stability of the sail? And one of the big issues we've had to wrestle with is managing momentum. If you have an offset of your center of mass versus center of pressure, and for the sail in the Near-Earth Asteroid Scout, which is roughly the size of most of this room and floor area, an offset of a few millimeters can cause us to lose control of the sail. So we have to be able to dynamically adjust the center of mass versus center of pressure. We're doing that, and we think we have an approach to manage that. And if you do that, you can actually maintain attitude and fly your sail. But it's a challenge. And I think that the community has had to really come to grips with, it's not just deployment, it's control. How do you control the sail? Now here's the encouraging news. There are a lot of people who have flown sails in Earth orbit. We all hear about the Planetary Society sail because they have a great spokesman, Bill Nye, right? And I don't want to do anything to diminish the great work that they've done. They've done a fantastic job in popularizing solar sails. But the first Earth orbital deployment of a sail was done by NASA. It was done in 2010, Marshall Space Flight Center, NanoSail D. It was a 10 square meter solar sail deployment test off a 3U CubeSat built at the Ames Research Center. We built the solar sail, and it deployed successfully in low Earth orbit and stayed up there for a few months. The Planetary Society came in, looked at our design, and basically took our design and increased it in size to 32 square meters, and that was Light Sail A. So they flew that in 2015. But they're not the only players. If you look at this chart, the first real interplanetary solar sail mission was flown in 2010. It was flown by the Japanese, a mission called Icarus. Icarus is a fairly large sail, about 14 meters on a side. They demonstrated controlled flight in interplanetary space. They had some instruments on board. To the best of my knowledge, it's still out there. They talk to it about once a year. It's not doing any science now, but they did fly it. I would have to question the choice of the name if you study mythology. That is not the name I would have picked for my solar sail, but they reverse jinxed it, and I think they were successful. Just last year, the European Union, not the European Space Agency, the EU space effort, funded a small CubeSat mission called Inflate Sail. I was the US COI on this, another Earth orbit deployment of a sail called Inflate Sail. Again, you probably haven't heard about Inflate Sail. They flew it, they took data, some papers coming out of it. We learned a lot about inflatable booms. But there's not been much else publicized. And the Canadians have flown a small sail. Over the next few years, there are going to be more. Paulette talked about Light Sail B, which is going to deploy and actually use magnetic torquers in Earth orbit to maintain attitude of the sail, and they're going to change their orbital elements and show that you can navigate. There's a small business, CU Aerospace, which will also be flying a 20 square meter solar sail this fall as a secondary payload on a Rocket Labs launch. It's going to be an Earth orbit sail mission. We have a Space Act agreement with them. They developed this as a part of the Small Business Innovative Research Program at NASA. I was the monitor for that, so we helped them develop this sail. And then there's the Near Earth Asteroid Scout, which I think is the groundbreaking sail for this community and for what we might be able to do in the future for solar sails. NEA Scout is actually funded by the Human Exploration Office at NASA. Go figure, right? Not science, not technology, but human exploration. And that began, the project began when NASA was actually thought we were going to go send people to an asteroid. And so there was interest in doing lots of multiple reconnaissance missions for asteroids. And how do you do that low cost? So we proposed, at the same time JPL proposed, a solar sail asteroid reconnaissance mission. Both proposals went to the same solicitation, had exactly the same name, and proposed roughly the same mission. So NASA headquarters, instead of King Saul cutting the baby in half, said, you two get together and make it one mission. And the way we decided to do that is JPL took responsibility based on the Marco spacecraft design to build the spacecraft. We built the solar sail and have completed that, and I'll show you pictures. I want to dispel a myth here, and this came out in the discussion a minute ago. Marco and NEA Scout may fit within a 6U CubeSat form factor. They are not CubeSats. There's almost no component aboard the craft that's traceable to any CubeSat that's flown or will be flying. These are fully functional, interplanetary, as rad hard as we can get them spacecraft, packaged in a 6U CubeSat form factor, okay? Headquarters thought we were flying CubeSats. They kept wanting to cut our budget. Why are you so expensive? Because our radio alone was $500,000, okay? We can't have a CubeSat budget and do a 2.5-year mission to an asteroid, right? So the good news is the NEA Scout total budget for development of an interplanetary mission that's going to do science in a slow flyby of an asteroid. We have a camera provided by JPL. It's going to do imaging of the asteroid and a close flyby. It's $23 million. Okay? Start to finish, we proposed it at 23. We're going to come in right around 23 to 25. We've had some delays. As you know, that always adds cost because of labor. So we're fairly inexpensive. It is risky. Everything's single string. There's not much room for redundancy in a 6U CubeSat form factor. This is roughly the size of the sail. So imagine in the floor of the room over here, this half of the room, our boot box solar sail, spacecraft sitting there, 86 square meter solar sail. We have 4 booms, a little over 20 feet each. that are going to deploy that from the central hub and pull the sail out that you've got in your hands. And we're supposed to launch as a secondary payload on SLS on the first flight when it flies in 2020. So we did a sail deployment test of several prototype sails. We've actually deployed our one-time deployment of our flight sail, pictured here. We've since started repackaging that sail to put it back on the spool to go into the spacecraft. Here are some pictures of the team and some pictures of the hardware. And what's illustrative is here is the spool around which the solar sail was folded and wrapped before deployment, and there it is on the table where we just basically had to get it off the table after we'd done our deployment work so that we can then lay it flat again and start our precision folding to get it back on the spool. So that tells you how much we can cram in there. I will say from a technology point of view, we proposed a larger sail, a 200 square meter sail, but they didn't give us a 12U CubeSat form factor. They gave us a 6U CubeSat form factor. So we packed as much sail as we could pack into that form factor. We could have built this sail quite easily to be 200 square meters and had much higher performance in terms of the sail itself. The NEA Scout, as I mentioned, is a 2.5-year mission. We are going to launch on SLS. We'll go into an elliptical lunar orbit where we will deploy the sail, trim the center of mass versus center of pressure, validate our flight and control algorithms, and wait for the right phasing for when our target asteroid is in the optimal position where it will spiral out of lunar orbit and go for the slow flyby. One thing about a sail is you can't turn off the thrust. It's a bad day in the solar physics community if we turn off the sun to turn off the thrust. So you have to balance your thrusting and your tack angles to get a slow flyby of your target. And we're going to fly by the target asteroid, 1991 VG, at about 10 meters per second is the target velocity for our flyby. In terms of where are we on the technology, I've been involved in this for a while. We've built and deployed large sails up at Plumbrook. All that went away when a lot of the technology money went away. Got all these small sat missions. I will say there is an opportunity that some of you may be aware of, others in here may be bidding on it, and that's the Salmon 3 mission of opportunity that was released a few months ago for technology demos for heliophysics that'll be doing a ride share on an ESPA with the IMAP mission. And I know of at least 2 to 3 proposal teams that are proposing against that opportunity to do large solar sail technology demonstration as their proposal in this competition. And of these 2 to 3 teams, the performance metric you need to see is the characteristic acceleration of the sailcraft system, because that determines the performance and what orbits and trip times that you have. A solar sail propulsion system is hard to separate its performance from the rest of the spacecraft. And I would say that the NEA Scout project, if it had been proposed 20 years ago, we would not have been able to fly it. And that's not because of the immaturity of the sail technology. It was because the spacecraft and avionics and components had not been miniaturized. Spacecraft mass is everything in a sailcraft. If you want to have good performance from a reasonably sized sail, you need to limit your expectations in terms of the amount of instruments you can carry and how much things can weigh. When I look at what Paulette just briefed a minute ago, I looked at her 150 meter on a side sail and found that that was over a 20,000 square meter sail. I do not believe we have the technology today to build a sail that's 20,000 square meters. I'll tell you right now, and I'll show a chart in just a minute, what I think we can build with technology scalable from what we're going to fly on NEA Scout, and we have flown in these other missions that I showed you, in a reasonable amount of time in terms of performance. I think you'll like the answer. Some of the missions that folks have talked about doing are probably doable after the next demo of a large sail. Hopefully one of these teams will be successful against this AO. And if they are, I think your mission sets will be enabled with a demonstrated propulsion technology, okay? But not all of your mission sets. There were some pretty ambitious wish lists that I heard today, or the last couple of days. So let me tell you from a polar perspective what I think we can do. If you look at this plot, it's a plot of the characteristic acceleration, which is the figure of merit for the acceleration that you can get at 1 AU of a sail system, sailcraft of a certain mass, regardless of the sail size. You can get this characteristic acceleration with a 22,000 square meter sail and a heavy spacecraft, or you can get it with something a little bit bigger than NEA Scout and a much smaller sail, okay? If you get this characteristic acceleration and you start spiraling in at a closer distance than 1 AU, get the higher thrust, you can get some pretty rapid inclination change rates with your sail system. If you look at where I think we can have demonstrated within the next decade, I believe we can get this 0.2 millimeters per second squared, maybe a little bit higher, which would enable you to have a solar sail polar imager mission with a flight time of a decade or so, and taking science all the while as you're going up from your initial deployment or near the ecliptic to that solar polar inclination. You could stop along the way if you have something particularly interesting at a particular inclination and you want to do longer observations, or you can keep cranking your orbit. What's nice about this is if the scalability continues, and after you fly this first science mission to do this, you're going to enable yourself to build ever larger sails. It's a learn how to make them a little bigger, fly them, see where the lessons learned are, and you can make them a little larger still. I would be very skeptical of anyone claiming to be able to build sails with much larger performance than that in the near term. In the sail community, there have been a few efforts that have been proposed and failed because, in my opinion, they underestimated the complexity of the flight system and the ability to deploy and control a large sail. And I think that when we went back in the early days of solar sail advocacy, we thought we could go from nothing to the SPI class sail immediately, when in fact what we need to do is learn how to crawl and then walk, and then we can do SPI, okay? Or something like that. If you want to go with the small constellations of smaller spacecraft, I think without too much of a stretch, that technology is in hand. We can do that. And I think these teams, if one is selected in this heliophysics Salmon 3 move, will show that. That technology is in hand to do that. Now, the bad news. The bad news is you people want to sit over the poles of the sun, okay? And you want to go up to 70 degrees and hover. No. We can't do that right now, okay? In order to do that, you're going to have not to have characteristic accelerations of 0.2. You're going to need 2 to 4, okay? An order of magnitude better characteristic acceleration. I do not believe we're anywhere close to that kind of performance. So I wish I could tell you otherwise, but I can't. So I think a solar polar imager, a high inclination imaging, there are all sorts of interesting things you can do with a sail. You can create your artificial equilibrium points at just about any location in an orbit around the sun. NOAA's interest in solar storm warning with this next generation solar sails, we can do sub L1 hovering along the Earth-Sun line to do advanced notice of solar storm warning. I think if you go back to this chart, that technology is now within reach thanks to what we're doing on NEA Scout and what these other groups have done with their Earth orbiting sails. Several years ago, that was not the case. It was too big of a leap. We were trying to go from nothing to implementation. I think we're pretty much there. So, I hate to say this, your hovering sails are still going to be out of reach. Does that mean it's forever impossible? Absolutely not. It's just we're not ready to reach that far yet. The other thing is, there is a way you could do your solar pole sitting, and that's if you're content having your sail sit at a distance of almost out to Jupiter above the sun's north pole with the characteristic accelerations we can have today. But that's pretty far away, and I don't know that you want to do that to get your polar positioning. But that's how far away the technology is today from being able to hover. That said, with these high inclination orbits, we could look at some very interesting orbital configurations, things like Milnaya types orbits that potentially get you a little higher than you might optimally want to do, but get you some pretty long hang times over the pole with a sailcraft. or a traditional half an AU, 0.48 AU resonance orbit, where you get significant times at high inclination. And again, that technology, I believe, is pretty much close at hand. So with that, I'll wrap up and take questions. Yep, just go to the mic, I guess. Oh, yeah.
Yeah, Les, Jeff Van Cleve from Ball Aerospace. A beautiful talk. It's good to see we're making progress on some logarithmic scale to big sales. Would it be naive to take your 0.3 millimeter per second squared characteristic acceleration and divide it by the inverse radial distance to the sun so that you would have much higher accelerations close to the sun and much lower out by Jupiter? Is that simple physics work, or is there some problem that gets in the way of that?
We're already doing that when we do our performance metrics. The characteristic acceleration is a way to standardize your performance measurement, and everything is pretty much normalized to 1 AU. But we're actually doing the calculations of a 0.4 AU mission, taking into account the higher solar flux with a sail that has that normalized performance characteristic. So we take that into account in the flight times I have here. It's already in there. The characteristic acceleration is just a way to allow us to do apples to apples comparison of different sailcraft.
So that's implicitly at 1 AU.
Implicitly at 1 AU. And then we vary the performance, the thrust performance of the sail depending on where we are. That's correct. Yeah.
Les, I have a question. What's the spacecraft mass for that 10-year mission?
It doesn't matter. It's the
Doesn't matter.
characteristic acceleration of the system.
Fair enough.
And so if you have a 12U CubeSat with one instrument, you're going to have a sail that is something that's not terribly large. If you have Paulette's 5 or 6 instruments, you're going to have a 20,000 square meter solar sail, which we can't build today. And so it really is it's a systems problem. If you only have 1 or 2 instruments and you can get a small spacecraft that's a 100-kilogram bus, a sail size that's of a few thousand square meters is absolutely doable to get you that kind of characteristic acceleration.
And then that Icarus sail satellite that you showed, that was about an order of magnitude larger and more massive than the other sails that people are using. What were there problems associated with that? Why are we not going bigger, faster?
It was a demonstration of solar sailing, but it was a brute force demonstration of solar sailing. The sail that they are flying is about 100 times thicker than the one I just passed around the room. Its characteristic acceleration was horrible. They weren't really trying to use, no offense to my Japanese colleagues who are listening and streaming this, I don't mean to diss the achievement that you had. It's a significant achievement. It showed the community and the world that you can do this, but they weren't optimizing or designing for performance. They flew this mission to have an existence proof that you could deploy and steer a sail, and they weren't really worried about performance to do anything with it.
Great, excellent.
Yeah.
Well, it's great to see the progress. Questions here? Paulette?
Back to your, this is very nice, Wes. Glad to see this. If you go back to your slide on the time to get to the polar orbit, was that, you had the graphs for 2 different distances from the sun. Did your 10 years and your 5 years include the time to get into the...
No, it did not.
Okay,
Because
so you first have to get into 0.48.
you do, and the reason I didn't do that is because you never know if a rideshare opportunity is going to give you a favorable opportunity or if you have to spiral out. If I were looking at doing this kind of a mission, I would want to get there impulsively to cut the trip time. And so I think that goes into your total mission study. It did not include the time to get to the point of departure. That was assuming you're at 0.48 or 0.5 and you start doing your inclination change. Yeah.
Any other questions? Yeah, Vic.
Does the material of the sail affect in any way measurements like by magnetometers, or does it charge? Is charging an issue there or anything like that?
We have some reports on about that and available in the NASA Technical Report Server. We did charging analysis of it, and we don't see that there's going to be a major issue. What we'd like to do, quite frankly, is put like a magnetometer out on the boom and have some measurements to confirm that. But there's some analysis that indicates that it may not be as big a deal as people thought it would be, but I'm not the expert in that, so I'd have to defer to the folks that did that analysis.
Okay. And by the way, are you going to return that sample to Roswell? You know where you got it?
You shouldn't say things like that on an open mic. No. That material actually has got an interesting history to it. It's been around for about 15 or 20 years, and it was the same material we did some of these early sail deployments on. And we did the long-term radiation tests of it. It holds up very well in that environment that you want to operate in. I wouldn't go much closer than what we're talking about here, but it's pretty good material. And it's a plastic, it's a polyimide. Don't need Roswell aliens to make that.
All right, great.
All right,
Thanks, Les.
Oh, are you up next? Yeah. Okay. Well, that makes it easy, doesn't it?
I'm sort of connected here.
This guy.
Put this on.
Make sure I get my sail back.
Oh, you got one, okay. Yeah, there we go. All right. Where's the laser pointer? Which one is it? Yeah, I'm going to take it down. Great. Okay. Thank you very much. So it's been a great workshop, really good discussions, and really, really productive. I'm going to talk today a little bit about a mission concept that a group of us have studied, which is, we believe, feasible now, ready to go now, either as a Pathfinder mission standalone, or potentially as one of 2 or 3 or 4 satellites in a larger constellation. But the point is, we think we've studied it well enough that the technology is ready to do now, so that we can make progress now. So looking at past missions, and lots of people have shown, Paulette most recently shown these different views. Ulysses, it was a great mission, fantastic results, but no imaging on it, unfortunately. But it had a great orbit, 6 years elliptical orbit with a 1.35 AU perihelion. For remote sensing, it's a little bit large and it's a little bit long, but they got amazing results, and they had a direct injection to Jupiter, and so that's one way, I think, a very effective way to do a polar mission. The Solar Orbiter mission, which has been talked about and we're discussing this morning, will, at the end of its extended mission, get up to 30 degrees. I think Paulette said it'll get up to about 30 degrees in 9 years. This is actually a plot of each time it does a VGA. There's a VGA here, it cranks itself up. So in 7 years, it's at 25 degrees latitude, and it gets up to about 32 degrees latitude after 9 years. So it's a large spacecraft. It gets in very close to the sun. It goes into 0.28 AU. So it's got a massive thermal protection system, but it's got a fantastic payload of remote sensing and in situ instruments. But the biggest challenge I think I see it having is the telemetry. It really just uses X-band, and so and it has to share all this telemetry with the 10 instruments. And then because of that telemetry and the orbit that it has, there's really only 3 remote sensing windows, 3 10-day windows. So it spends at the highest latitude at the end of its 10-year extended mission. It'll get 10 days of maybe 10 or a few days at these highest latitudes, but but not that many. But it's getting ready to launch, hopefully in 2020. It's scheduled right now for February 2020. We'll see if that happens. The backup launch is October 2020, and it's ready to go. It's going to go along with with Solar Probe, which is now flying, and we saw great results from Solar Probe. So, these are just some images of all the reasons why we want to do this, and this whole workshop is centered around a polar mission, so I don't really need to explain these or talk about these much anymore. The one mission that Dan Seaton forgot to talk about is called the SPICE instrument on Solar Orbiter, which actually is an imaging spectrograph that will measure velocities of flows coming out of the polar coronal holes. But, fundamentally, a polar mission is a mission of discovery. And I think, as Bob Ergen said yesterday, many fields in heliophysics, but in science in general, kind of work their way incrementally with a Pathfinder type mission, and then you go to a second generation and a third generation mission. And so, I think this ambition to go to the poles and the things we want to learn are scientifically compelling. And we've discussed and are discussing lots of different mission types. And a couple of them have been discussed, and there's a few more that are going to be discussed after me. So, just to kind of review them, Paulette talked about solar sails, so did Les. Solar Polar Imager utilizes solar sails. There's pros and cons to them in terms of readiness. There's a lot of technology that needs to be developed. I think that's another thing that we really have to remember and keep in mind as a community. I think as we go forward, we really want to try to identify the technologies that we need to improve and enable these future missions. Certainly the solar sail technology is one that's being identified, but clearly also laser comm, we talked about that. I think Jeff mentioned that earlier, but these large data pipes, if we really want to get this lots of data down from far distances, we really need a larger data pipe. The Chinese are studying a mission called SPORT, which uses a lot of Venus gravity assist and Earth gravity assist to crank its way up. Jeff's going to talk about, in a little bit, after the break, I believe, Jupiter gravity assist, similar to the mission that Solaris that I'm going to talk about, the mission concept, where he uses ion engines to circularize the orbit. But it's a large spacecraft. It's 700 kilograms. It's a whole suite of instruments, very capable, extremely exciting, but long term. I think Spock, I think, is a constellation of satellites, also relatively large. But I think the concept of constellations of satellites is one way to get you continuous coverage. No one's shown this slide yet, so I thought I'd show it. I don't need to talk too much about it, but this is courtesy Yuri Tumre. He showed us a couple of months ago, and I said I got to use that, particularly when I give public talks. But this is part of the motivation for going to the poles. Carl certainly appreciates that, and all of us. So there's also different types of science we have been talking about doing. Some of the science we're talking about doing takes long time series of data. We've seen results that take 2, 3, 4, 7 years of data from HMI or MDI to get these results down at the tachocline and down deep, deep in the interior of the sun to see these solar cycle changes. But there's other objectives which can be done quicker. This objective, this idea of you having multiple vantage points, whether it be from a solar polar mission, and I list a whole series of them. Tom expressed his skepticism about using GONG as the other spacecraft as an Earth-based asset, but you also have SDO, where you could have the Lagrange L5 mission, which is being planned by Europe, which will also have a magnetograph, Dopplergraph. Also, Solar Orbiter could be that other position. So, the type of science, if you can get, we need to study very carefully what the requirements are to go deep and how deep you can go, and obviously the longer your time series, the deeper you can go. But probing this internal structure is one of these unexplored regions, and it's kind of the holy grail. So some of these questions are easy, some of these are hard, but relating the subsurface flows, subsurface and surface flow patterns at the poles, the questions about the polar vortex, what are its characteristics, mapping it out, where does the meridional flow return, where does it behave at this singular point of convergence, all these types of questions. Some are easy, some are hard, but these are the types of really big questions that we want to be addressing. Also Scott talks about, the solar activity, on the surface, just looking at bright points or just the flow of active regions. But, the distribution of these structures as we go towards the poles are going to teach us a lot about the solar activity and ideally the understanding the solar cycle. You know, other missions, larger missions that have a spectrograph on them can actually measure directly the outflow from these polar coronal holes. And then I guess this is one of Scott's plots here, plotting the solar cycle as it converges down. And so, you know, questions about, you know, how does the polar field determine the strength of future cycles? You know, this question of north-south asymmetry, we talked about that a little bit this morning and yesterday. I think that's a big deal. But, you know, trying to understand these mechanisms of polar field reversals as cycle predictors or precursors, I think is, you know, these are big questions. Some of those we can answer easily and quickly. Some of these, you know, might take a longer time and aren't going to be in the 3-day Thomas-Zurbuchen domain. But one thing that clearly is in the Thomas-Zurbuchen domain is this view, and many of it talked about it, so I won't dwell on it too long. But, you know, when you're over the poles, every CME is a limb CME. And that, you know, I'll say it again, every CME is a limb CME because we don't want to minimize that fact, that point, because you can study the longitudinal extent of these CMEs, the dynamics of them, so much better than halo CMEs that we would see in Earth orbit coming towards us. So even if we had a month or 2 months or a couple of orbits watching these CMEs, even at solar minimum, you get, you know, basically 1 CME a week. Well, maybe it's a little runt CME, but it's still a CME. You can still learn physics from it. It doesn't have to be a Carrington event to learn about the physics of CME eruption. So this polar view for just, you know, the coronagraph and white light imaging is going to be spectacular. And you know, Sarah coined this phrase, the sunny side up fried egg view. You know, this is a model of it, courtesy Olga Panasenko, who couldn't be here today. But, you know, this is, you know, the way you could study the structures and, you know, ephemeral pseudostreamers and you know, the longitudinal extent of all these different types of structures, not only from a pure science point of view, but clearly from a space weather point of view, are things that are enabling observations, if not something that we want to be able to set up long-term and study for and strategize for in the future. So this mission concept that a group of us have studied, Jeff and myself and others, is the idea is what can we do now that the technology exists today? And I'm talking about not just the orbital technology, but the thermal, the telecom, the power, you know, all the elements that make a real mission. You know, what can we do today? And you know, we've had a lot of progress in terms of miniaturization of instruments, as well as improved and lower cost on launch vehicles. So, you know, we took a Falcon 9, which is currently, you know, the go-to workhorse for launch vehicles at a quite affordable price, and we said, okay, you know, what can we do that can get us a polar mission, you know, in a 5-year time frame and not have to wait 10 years to get the technology ready and then another 10 years to get it out there. So if you follow the Ulysses idea, Falcon 9 with a Star 37 can get a small sat, and this is basically a small sat solution. So if you had a really big rocket, if you had one of the BFRs that Elon's going to build down the road, you could put 4 of these on it, and you could send 4 of these out to Jupiter. But right now, the Falcon 9 with a Star 37 can send 1 small sat out to Jupiter, direct injection to Jupiter. You get out of the ecliptic, you get up to, say, 75 degrees inclination, which is a number that a lot of folks have talked about, and that comes back to the sun, so you get your first polar pass in well, if we launch in, say, 2025, October of 2025, the launch window going to Jupiter is about every 13 months. So you could launch it in 25, you could launch it in October 25 or in November 26, et cetera, and so on, depending upon when your opportunity occurred. But if we launched in October 2025, we'd be over one of the poles in the early part of 2029, which is actually the same time that Solar Orbiter is going to be at its 30 degrees highest latitude. And then the thing that we do with this mission, because we're trying to do it on the cheap, we're trying to do it as a small sat. Jeff's using ion engines for his large spacecraft. He uses these 2 Next engines, which are very powerful. But we're going to just use a Venus gravity assist and use Venus to slow us down, to circularize our orbit, so that with the second orbit, you know, we start out at Jupiter, and Ulysses had a 6-year period. Well, we start out at Jupiter, but then we circularize it using Venus, and so the second orbit would have a 3-year period, And the third orbit, using another VGA, would have about a 1.5 to 2 year period. So you could get, say, 3 polar passes in the course of, 3 to, 4.5 years. And basically, this is a plot of solar latitude, the orbit in terms of solar latitude and distance from the sun. So we're coming in, we start out at 5.5 AU, we come in to 0.72. The other advantage of staying only at Venus, a lot of people talk about a mission that goes into 0.5 or 0.2 or 0.3. Then you got all the problems that Solar Orbiter has with the thermal issues. Then you have a huge thermal protection system that you have to enable. Even 0.5 AU is a pretty extreme thermal environment. But if you stay out at Venus, that's only a factor of 2 more than you get at 1 AU. And we know we build design instruments all the time that work at 1 AU. So we take this mission in only to 0.72 AU, and we operate it in the range of, well, this plot shows that we get about 75 days above 60 degrees latitude over each pole. And that goes from a range of about 0.9 AU out to about 1.5 or 1.6 AU. So this is a plot that maybe is a little easier for us to visualize. And this helps you understand in terms of the discussion this morning. Do you need 100 days above 50 degrees or 60 degrees latitude to do your helioseismology that you want to do? Or, how many days do you really need? So basically with this orbit, if you go, the point A and point D are the 50 degree latitude points. And with this current orbit in the first pass, you get 120 days above 50 degrees latitude. You get 75 days above 60 degrees, whatever that magic number is, you have those options. And so you design your mission around what you need. You do the same thing in the South Pole, and since you're circularizing with your Venus gravity assist, you actually get tighter and tighter, and you don't have to go quite so far out. So studying the spacecraft and studying the, what can we actually build that can do the science we want to do, the real challenge for this type of a mission is, Ulysses had a RTG, so we can't afford that. We don't have those access to those, so you have to use a solar panel. Our feasibility study, shows that you could do this with about 11 square meter up to 16 square meter solar array, which is not that big. This is kind of a scale size view of it. So if you had a 1 meter or 1.2 meter size spacecraft, the solar arrays, this is just a configuration of it, but these are ROSA. This is based on a concept of a ROSA array, which rolls out, and this is basically your 15 square meters. And so when you're out at Jupiter, this figure shows when you're out at Jupiter, you have your array perfectly normal to the sun to get the full power from the array to keep your instruments alive, to keep your heaters going, to keep your instruments alive. And then when you get into the sun, you feather it back so that you're at, say, 60 degrees angle to the sun. So you don't have the full illumination on the arrays. You don't cook the arrays, but you can still operate it because you're only going into 0.72 AU. You can survive that. So the question of what instruments you want to put on it, that's another open question. This talk is really just about a mission concept, and it's really up to the community to think about what the right instruments would be, what we would want to fly. Clearly, a Doppler magnetograph is one that's ranked very high. I think the coronagraph or heliospheric imager, there's a debate about which one takes priority, whether it's for operational space weather or for science. The EUV imagers. Then there's lots of discussion about irradiance instruments, the irradiance spectrometers, a UV spectrograph, and then there's the in situ instrument package. So, that's starting to sound like Solar Orbiter's payloads complement. So there's several ways you could approach that. One is if this was one of several spacecraft, you could have them dedicated. And I think this was mentioned earlier, you could have one be a dedicated remote sensing 3-axis stabilized platform. Another one could be a spinner for your in situ instruments. But, fundamentally, it depends on what the resources you have for your mission as to what you're able to do or what's enabled for this type of a mission. So if you go back to science questions that one could address, and we talked about this at the end of the day yesterday, what would be your top science priorities you'd like to do? Well, there's these really big ones that we want to do with the deep helioseismology, which requires these long baselines, but maybe with 120 days over inch poles or 75 days over inch poles, you can get down to a certain depth to answer some important questions. There's lots of things about the surface and subsurface flows which we can answer with this type of a mission. And some of these objectives require longer, larger spacecraft, maybe multiple spacecraft. Yes, others can be done with a single spacecraft with a couple multiple flybys. I think the beauty of something that, even if you only get, say, 3 or 4 months per pole with each of your passes, and then you repeat that 3 years later, and then you repeat that again 1 or 2 years later, you're taking a sample as a function of time in the solar cycle. So you're getting a pretty good baseline of observations to do some helioseismology, and you get, at the pole, it's about 36 days for a solar rotation. So with a 75-day baseline, you get basically 2 solar rotations at the pole, and you get that over each pole, and you get them quickly over each pole. So the north-south asymmetry, you get a good handle on those types of questions. And then you do that 3 years later at a different time in the solar cycle, and compare that to a different time in the solar cycle. So I think fundamentally, as Bob Ergen said, a field, like magnetospheric physics or heliophysics, solar physics, it's an evolution. And I think we want to make sure we don't try to design the perfect mission, which is going to take us 30 years to develop and get advocacy for. I think we've never been to the poles. This is discovery space that is going to revitalize our field. So we want to get a pathfinder up there. We want to get some science out of it. We want to validate some mission designs, and then the next generation can perhaps will be a constellation of these or a larger satellite, or other design configurations, but there's clearly technologies that that come into play. But there's good examples of this. TRACE led to SDO. We didn't just build an SDO. And I think even who was it this morning from Air Force, Carl, I think, was saying the Air Force isn't going to buy something unless you've validated it a little bit, unless you've shown that it kind of works. IBEX turned into IMAP. Image turned into MMS. I mean, MMS is huge, and that's what Bob was talking about. But it started with the image satellite. So anyway, I'll just end there. I think this concept is a pathfinder type of a concept, and I guess my point is we can do this now, and it's ready to go. And the other thing that for doing something now is that you could fly it at the same time. If we flew this now, it could be up at the same time that Solar Orbiter and Solar Probe are flying. So we would be able to get these different vantage points, and we wouldn't have to rely on Gong to get that second vantage point. And we'd rather do something now than wait till we're retired 15, 20, 30 years from now. Thank you.
Hey, very good. We have time for 1 or 2 questions if anyone has any. Just go to the mic if you would.
You say the interval to Jupiter is 13 months. Well, yes, I know that interval to Jupiter is 13 months. The question is, do you need a more precise interval if you're going to do the Venus assist afterwards?
Not really. Not really. There's enough play in the orbital dynamics. You can make it work. Yeah.
Any other questions?
In fact, that launch window, 13 months, you get about a 1 month, at least 1 month window where it's quite easy to do with, even with the Falcon 9 vehicle.
Okay, Paulette, last question.
I feel like I should know the answer to this, but why did you pick an inclination of 75 degrees? You
Right, okay.
optimize that?
Yeah, so you want it high. I mean, ideally, you'd go to 90 degrees.
Why not 90 degrees?
Why not 90 degrees? Okay. So you have a given launch vehicle. It's driven by your spacecraft mass. The lighter the spacecraft mass, we could send it higher latitudes. But we viewed 75 degrees as a good target for the science because that gives us, the 100 days, 120 days above 50 degrees latitude or 60 degrees latitude. If you had a smaller spacecraft with the same launch vehicle, you could go higher.
All right, thank you very much. Our next speaker is Neil Hobart, and we're running over a little on the agenda, but he'll have his full 20 minutes, and then we'll stop for our break. So,
Right. Okay. All right. Okay. Well, to start off with, I submitted a very generic title that I'm using for the AGU, but I've updated it. So instead of space weather, we're going to talk about off-axis missions. And I don't need to justify it because we've justified it enough all yesterday. I have a very simple outline. I'm going to talk a little bit about coronal EUV observations. Mostly just there was some conversation about that before. That was my question about what do people want to do with the EUV imagers. I'll talk briefly about that, but I'm going to spend most of my time talking about magnetographs. So for the tomography fans, one of the things we've been doing recently with SUVI, NOAA asked us, Lockheed, to sort of explore the ideas of what would we do if LASCO were to disappear. So one of the things we said we could do is do a wider field of view sort of raster. So we've been doing mosaics of the using both the GO16 and GO17 versions of SUVI to look at the sun in like this a 9-panel display here, the standard set image here. So we go out a little bit over 4 solar radii. Now SUVI wasn't designed to do this. So, but one of the advantages it has over AIA is that the mirror is highly polished, so it has lower scattered light. You can see dimmer things. The one thing that's not designed for is to point off axis, so there's baffling issues. So there's a lot of stray light. This is highly processed by Dan Seaton, trying to remove as much of that stray light as possible. But we found that you could actually see signals well above the noise all the way out to the edge of the field of view, even in a quiet sun condition. So the idea that you could actually image the middle corona seems quite feasible. And so if you wanted, what they call tomography or some sort of stereoscopic reconstruction, this is an opportunity to sort of capture the entire magnetosphere of the sun, essentially, within a single imager. And there's 2 instruments that are sort of thought about. One is we could actually build modify SUVI to take on this field of view. And there's also the COSY instrument that's being developed by SAO that could look at similar fields of view. It looks like it's actually promising for doing images within the corona. Here's another fun one. We spent a month trying to see a CME. This is not a good time of the cycle to look for CMEs, but we found one little tiny one. You can see it actually gets out here, depending on how well you can see. There's about 3 solar radii that we can actually image it. And this is not as well processed as the previous image, so we think we can do better than that. We think there's signal going all the way out here. So it looks like we can capture CMEs coming off. If, maybe someday there'll be a big enough one to do it. And I believe, Dan was telling me yesterday that there's talk about making this a standard sort of product to come out of SUVI, maybe. There's a debate about that. So that's the short segue out of UV into magnetographs. Here's magnetographs we all know and love. Here's the concept of MDI, and this is a photo of HMI with its lid taken off. These are both spent 20 years in operations combined, and they're sort of engineering marvels in a sense. They got complicated optics. They have to survive the launch with these very precise calibrations. Survive in space. So there's a lot of very precise engineering that goes into this. And they sort of, the order of, HMI is a sort of a beast at 46 kilograms for just the imager, and another 42 for the electronics. And so this is a great instrument, as we all know. It's showing its age at the moment, so if people would want to vote for a new HMI, now's your opportunity. But it's not really geared towards something you want to send off into deep space, or off to, you need small sat. It's not a small sat solution to anything. So a couple of years ago, we started looking at reducing this down. Oops, push the right button over here. So we came up with what we call the compact imager, and it's really just a shrunken HMI. So we took the same components, these are all the same components, shrunk the optics down to, instead of a 14 centimeter, a 7 centimeter entrance filter, right, entrance aperture, and all these components are the same. So it's sort of at TRL 5 already. It's already essentially ready to be built if we wanted to build it. And so we think this is capable of going, it's sort of designed, it's the same scale as some of the other instruments we send to deep space, about the same size as MDI, so it's something that's already been to L1. And then we started talking about, well, what could we do further? And the main point is that this is essentially using the same components. And if we go smaller than this with this design, we have to redesign the components. We lose all our heritage. And we essentially almost start over again. So we started thinking recently about what else could we do? And this is what we came up with. This is our new concept called image, or micro, and it effectively replaces this entire optical package with something the size of the entrance aperture of the telescope using photonic integrated circuits. So in the ideal world, if we ever take our compact magnetograph, it would be 1,000 times reduction in volume and 100 times reduction in mass. Essentially, it ends up being a silicon wafer about 7 centimeters in diameter. Can't quite get there yet. But we can, essentially these circuits are already operating in the telecom industry. So this is just leveraging what's going on in the industry. They operate typically in the 1.5 micron range. And it turns out there's a good magnetic line in that range, 1.5, where is it here? 1.564, 65 nanometers. So the idea is we're now exploring to develop this concept using that line. Essentially, it gives us, with a ring that's at 9 centimeters, we can get down to about 3 arc seconds of resolution. And we can believe we don't know so sure, since we haven't built it yet, we haven't really fully validated the numbers, but we think we can get down to the sort of something on the order of 40 Gauss with sort of 10-minute cadence, and I'll talk a little bit more about why that is. But the result is we end up with if we were to take, again, our dream instrument, our compared to micro, we drop from the CMI's version of 22 kilograms down to less than a kilogram for the optical package. Now this is built on something that Lockheed's been working on for a while called SPIDER, which is a segmented planar interferometer. I forget all the acronym, all the pieces of it, but it's essentially just a direct imager. It's not trying to do a magnetograph. It's started off with, it was demonstrated a couple years ago with just a simple 50 by 50 element integrated circuit. They were able to reconstruct an Air Force target, and this is kind of blurry, or not so clear here, but this essentially is an image from a railroad yard. They have certain applications they're looking at for using this. So that was demonstrated a couple years ago. We've recently they've had funding from the Earth Science side of NASA to look at another imager. So they're scaling up right now to a 200 by 200 element system that hopefully is going to be done by the end of the year, called SuperPIC, and they're intending to scale up to about a mega element things in the next few years. Oh, there's the acronym. Segmented Planar Imaging Device for Electro-Optical Reconnaissance. So anyway, this has been underway for a while now, and we're just piggybacking on top. So I sort of went through this fairly quickly. Just in summary, here's essentially 3 instruments we can now sort of propose, depending on the sort of the mission you're thinking of. If you're, I still think we need to have something like HMI up there. Just here's its capabilities. Compact magnetic imager we could build now if there's missions that are about to go now. But give it a few years, we can get down to something that's dramatically different. And beyond that, we hope we can get into the optical range. Another reason for staying out of optical is that the way these integrated circuits work, there's waveguides, and the roughness of the waveguide is the controlling factor of what sort of wavelength you can get to. So as you scale to shorter wavelengths, the scattering goes up as a high power of the wavelength. So essentially, you lose you need something really bright. That was one of the things they said, we need really bright thing to look at. We said, hey, we got a bright thing. It's pretty hard to find anything brighter. So yes, everything's sort of lined up that looks like it's a good match. So with that, you can choose your orbits you like. Here's some fiction things I threw out last year. Whatever orbit you want, we can sort of go there, because essentially we could become something that is ubiquitous. We have ubiquitous magnetograms. Put them everywhere. Who cares? They're small. One of the advantages, once it's designed, we're not building it, we're printing it. So it's not expensive. The optics becomes cheap. The electronics is a challenge. So that's something that we're working on, because there's a lot of computational imaging involved in this process. But so in terms of summaries, going back to the EUV, you could, an extended coronal imager could be something that complements a coronagraph. It provides some sort of tomographic capabilities. Magnetographs, where you can expect dramatic reductions in swap in the next few years and cost. And yeah, let's put them everywhere. Thank you.
Questions?
Very exciting. So why do you say tomographic reconstruction? Is that with the sun's rotation? Or did I miss something there?
You missed something there, yeah. I was being very generic. If people had mentioned tomography, and I thought,
Okay.
let's put something at the pole to be to do tomography. You're right. If you're really going to do it, you'd have to do rotational. But I think having something out the axis would still be a benefit. Right?
Any other questions? Okay, seeing none, I guess it's time for our break. Sarah, when do we come back? Oh, we got one. Oh,
Got a
okay.
customer.
Very nice, Neil. The EUV imagers, to get out that distance, you have to do two separate exposures, a long, deep one, and then,
Oh, the way we did this one, that's the way it operated. We had sort of 10 times the exposure. Even in our first test, we did even longer. But the other way to do is you can sum. You don't do it's 2x2 summing pixels. And if we were to build a real instrument, you could just have some variable sort of summing on the chip.
and then the CMI, you're building that up. I mean, TRL5 means you have a piece
Well,
of hardware.
essentially all the components are there, and we have a design, and we're ready to build it when somebody sends us a check.
Very nice.
Yeah.
What time do we reconvene? 3:30? All right. It's time for a break. Thanks.
Okay, so Chris is going to be talking to us about open magnetic flux and coronal holes probing the polar regions.
Okay. Can you guys hear me okay? Okay. So this is work I completed in graduate school. So I haven't touched this work in quite a while, so I apologize. Some of the slides are a bit old, and some of you guys have probably seen these slides quite a few times. But I'm just going to go back over this, especially with the focus on polar observations. I figured this might be helpful to go over. And so again, this was work I did at Montana State University. Currently, I'm here in Boulder at Southwest Research. So this isn't work I'm doing right now, but it's more of a side weekend kind of project that I work on from time to time when I have time. So, okay, so coronal holes. We've already had a lot of good overview of what they actually are. Dark patches in EUV and X-ray. They're dominated by a single underlying magnetic polarity, and they connect with open field lines, so they say. Coronal holes in our knowledge. We really want to know how, one of the goals I had, or several of the goals I had going into this, was to understand how coronal holes evolve across solar cycles, how they evolve across all latitudes, not just polar ones, not just equatorial coronal holes, but across the entire sun. And then how can we use these polar observations to improve estimations of open magnetic flux? So the methodology, I think a lot of you guys have seen these slides way too many times. Basically, we do a thresholding technique, segmenting so taking a full disk image, cutting off everything off the limb, breaking it up into a couple different regions, doing a thresholding technique to find a good threshold value for that particular field of view, and then we basically take a look at the underlying magnetic field to throw out filament channels, because otherwise not all dark features in EUV and X-ray are coronal holes themselves. And so we do this with each of our instruments. So we are looking at EIT data, we're looking at AIA data, and we also are incorporating stereo data as well. For this particular time period here, we're taking a combination of AIA and EUVI data and stitching that all together into one map at a particular snapshot. But I think the difference in our method here that we're using is that we're doing the actual thresholding on instrument-specific images and then stitching those boundaries together after the fact. So again, the data sources, we're using EIT, MDI, AIA, HMI, and also the stereo A and B EUVI imagery. And the advantage is that stereo A and B are traversing around the far side. The other benefit, and getting into the polar aspect of this, is that by taking advantage of EUVI data, we can get a sneak peek basically around at either side of the pole. So here I'm just plotting in a terribly too small font, I apologize about that. The spacecraft B angle. In white is for SOHO EIT, orange here is AIA, and then blue and red are stereo A and B. And so you can see if you're just using EIT imagery, if you're just using EIT imagery, you end up with large gaps in polar coverage if you're trying to observe over this entire period. By introducing data from stereo spacecraft, you're able to fill in a lot of those gaps in the polar coverage. And that was something that we discovered as we went through with this data. And the angles here, the spacecraft B angle varies between -8 and 8 degrees over that time period. Again, I apologize for the tiny text. I was in grad school. I didn't know any better when I made this figure. Okay. Taking a look again at just mapping these onto a sphere. These are two sets of coronal hole maps from EIT. The left is Carrington radiation 1925. The right is Carrington radiation 2000. And you can see that, again, we have some small gaps at the poles. These are self-imposed. We're basically just cutting off at the limb because we don't trust that data. Even with stereo A and B at this particular time frame, we still have some gaps at the poles, but it's not terrible. But really, this is sort of the figure I wanted to get to. And again, it's a mess of a figure. This is the main focus that we want to focus on here. Again, the time range is from 96 until 2014. This is just a sign latitude map of coronal hole coverage. So for every pixel here, at that point in time, and at that particular latitude, it's what fraction of that latitude and time is longitudinally covered with a coronal hole. So where it's maximized, you're getting a lot of longitudinal coverage, such as at the poles, and at lower latitudes, you're getting a lot more sparse readings. But this is sort of the main takeaway, is that, oh, and again, I've plotted red lines here at this magic latitude of 55 degrees, just to demarcate.
Move on.
Okay. I like using 55 degrees for that. It actually, when we plotted on top of this, we found that it really did well describe sort of the demarcation between what we saw as our polar coronal hole boundaries and our lower latitude ones. So you can see sort of the extent in EIT here is pretty actually well guided by that line demarcating the polar regions. But you see this sort of cyclic variation. And if you look back at the data, obviously the coronal holes are not popping in and out like that. It's actually due to the spacecraft B angle. Again, EIT is getting a better view of one particular part of the pole when it's missing the other part, and it just continues to cycle on. If we then incorporate, sorry about the microphone too, I don't know what's going on. Okay, if we incorporate AIA and EUVI data, this box here, you can see a lot of the problems are resolved in terms of having that cyclic variation. So whereas, say here, you're getting a blob, a blob, a blob, a blob, all of a sudden now you have a lot more continuous coverage of that polar coronal hole. And getting that different angular perspective is helping a lot with that. Okay, and again, that's just a zoomed in map of that particular orange box. And again, you can see it's more of a continuous sort of range there. Okay, so where we really see this again is if we break this down into a measure of open flux. So here in white, I just have from a model, just a simple potential model, using Wilcox solar data to map that out, the total open flux. If I then plot our inferred open flux from coronal hole boundaries, so we've taken coronal hole boundaries, taking the underlying magnetic field from MDI data, and then calculating a coronal hole enclosed open flux. That's the red curve. It's a lot less than what we'd expect from our model. If we then take our AIA and UVI data, that's the blue curve here, it does jump up a bit closer to what we'd like to see with our model, but not quite far enough. And if we take basically Omni data, so we're taking at 1 AU, taking that, assuming a nice uniform sphere, and converting that into an open flux, we end up with the orange curve, which again is a bit higher than everything else, but that was something I never had time to go back and take a look at. But where it really breaks down is if we decompose this total open flux into a latitudinal open flux. So in this figure, I have the northern pole above 55 degrees. I have the southern pole below negative 55 degrees, and in between in this panel. And again, the white is the same model data. We then plot our EIT data. You can see again this variation is mainly occurring in the polar regions as we expected, and the enclosed flux. And when we take a look at our AIA UVI data, again, you don't see that same variation over those time periods. So that's really where a lot of that missing open flux in that earlier panel is hiding away in terms of just not having polar coverage for these particular maps. We also did work with building a simple flux transport model to try to get a more accurate representation of the flux at the polar regions to try to feed back into our coronal hole observations, but that was sort of a side project that we didn't take too far. So again, back to the question of what I would want from sort of a polar perspective missions. Obviously, I'd like polar observations for both poles. 360-degree observations would be fantastic. At that point, you just build a Dyson sphere around the entire sun and just get all the light coming out. That would be great. But the main takeaway, at least for what I'm interested in this, would be EUV images to capture coronal hole boundaries of the pole. We got around some of the sort of the wall effect by taking a look at from multiple vantage points to the stereo spacecraft. You can sort of get a little bit around sort of that wall effect, but still getting out of the ecliptic would help a lot with that. So again, EUV images would be great, magnetograms would be fantastic, so that seems pretty standard. Continuous observations, having simultaneous north and south observations would be great. And the 3-day insight, I need to think a little bit more about that. So basically, there are lots more things I want to do with this when I actually have the time. Like I said, it's been a weekend project. I've been revamping it as Shortle. It's the Coronal Hole something. I forgot the acronym I came up with. But I'm revamping all of my code into Python and actually making the data really available this time instead of sitting on a hard drive back in Montana. So hopefully that'll be something that once I start getting snowed in on the weekends and I have time to do this, that'll be great. So that's basically it. Thank you.
Hey, questions?
Hey, Chris.
Yes.
Good job. Can you go back 1, 2, 3, 4, 5 slides to the plot I call the double helix plot?
This one?
Yeah.
Okay.
The red and blue thing,
Yeah, okay, yeah.
right? With the really crappy sign latitude distribution, because that's what everybody does, right? No criticism to you.
Oh, yeah.
What would be awesome is to see a time differentiation on that plot, right? You've got all the coronal holes encoded there, but not their lifetimes.
Yes.
So I bet that picture cleans up considerably the minute you associate a lifetime with those features. Like I was saying, which ones are to do with active region diffusion and which ones are not? What patterns are presented by each? My bet would be the ones that are to do with active region diffusion would appear to be moving poleward.
Right.
But the ones that are not would go the other way. But right now you're looking at a superposition of both. So I think that's very important to establish. So I would encourage you to keep going, and anyone that's in a funding agency in the room that gets a proposal on this to fund it. Thank you.
As long as we're on this slide, I'd like to point out that these sign latitude plots actually highlight one reason we need this mission, right? Everybody hides the poles down in the last 0.15 of the sign, but in fact, they're probably just as important as everything else, right?
Yeah, I mean, so the reason I started using sign latitude was in terms of computing areas. I converted all the maps into that so that I would have an equal area pixel, but then that sort of just propagated forward with everything else. So, but. Okay.
Okay, if we have no more questions, let's thank Chris again, and we can break for lunch.